The continuous time Fourier series or CTFS is used to find out the spectrum or the frequency components in a continuous time periodic signal. You have to keep this idea in your mind, right? So we are analyzing the continuous time periodic signal using the CTFS or continuous time Fourier series, right? So let us take a periodic signal and try to express it as a sum of harmonically related complex exponential. This word is very important, right? We are trying to express a periodic signal x of t as a linear combination of harmonically related complex exponentials. So that led to the beautiful equation of continuous time Fourier series equation, which is known as the analysis equation. So let us go into the video and watch how that can be done.
Actually, the continuous time Fourier series or CTFS is used to find out the spectrum, right? Spectrum or frequency spectrum of the continuous time periodic signals, right? Periodic signals, right? You have to keep the idea in mind that we are dealing with continuous time signals, and since it is Fourier series, actually we are talking about the periodic signals, right? So continuous time Fourier series is dealing with the spectrum of continuous time periodic signals. How to find out the frequency components present in a continuous time periodic signals, that is what we are trying to do. So let us take the case of a periodic signal x of t. So if the signal is periodic, we can express it like x of t plus capital T0, which we have discussed in the first unit, right? So for all t, if this case is satisfied, then we can say that the signal is a periodic signal, right? So where what is T0? T0 is known as the fundamental period, right? Fundamental period, right? And also we can express the fundamental frequency as 2 pi by T0, and this is the fundamental frequency, right? So fundamental angular frequency. This is not linear frequency, angular frequency. Okay, and which can also be expressed as 2 pi f0, which can also be expressed as 2 pi f0, where f0 is the linear frequency, right? Linear frequency, right? So these are the relations, right? Periodic signals, any periodic signal is starting at minus infinity and it is going to the plus infinity, right? So periodic signals are everlasting signals, which we have already discussed in the properties of periodic signals, right? And if you forgot the ideas of periodic signal, I request you to go and watch the videos on periodic signals, right? Now let us consider a complex exponential signal e power j omega 0 t. So you have to be very careful about this signal. This is not e power st, it is e power j omega t, e power j omega 0 t. You have to keep in mind that here sigma is equal to 0 and omega 0 is the fundamental frequency, right? Omega 0 is the fundamental frequency, right? And you can get harmonics of the signals. What is meant by harmonic of the signal? Okay, so let us go to Desmos and see what are harmonics of the signal, right? So now you can see we are in the Desmos background, and here y1 is equal to a1 sin x is the fundamental frequency, right? Y1 is equal to a1 sin x is the fundamental frequency, right? If I am increasing the frequency of the signal to 2x, here you can see it is a2 sin 2x, right? So what happened here you can see by the time the red color signal, the fundamental period signal completes one period, a2 sin 2x is completing two periods, right? So this is meant by harmonics, right? So this is the first harmonic. This is the first harmonic of our fundamental signal. The red color signal a1 sin x is the fundamental period signal, right? And this green color signal is the first harmonics. Why it is called first harmonic? Because it is completing two periods by the time our fundamental signal completes one period, right? Now coming to y3, if you carefully look at y3, you can see that by the time the red color signal finish one period, the black color signal, that is y3 is equal to a3 sine 3x is completing 3 cycles. So this is the second harmonic of our fundamental signal a1 sine x, right? Now coming to the fourth signal, that is a4 sine 4x. If you carefully observe, you can see that by the time the red color signal a1 sine x completing one period, the violet color signal a4 sine 4x is completing 4 oscillations, right? It is completing 4 oscillations. So this is the third harmonic of our fundamental signal, right? So here you can see that the starting and ending of the signals are same, right? But how many times it is completing the oscillation? So that is what harmonics means, right? So we can create harmonics of this e power j omega 0 t by multiplying this fundamental frequency omega 0 with a constant k, right? If you multiplying the fundamental frequency omega 0 with a constant k, we can get the harmonics, right? So let us have some harmonic signals, right? Phi k of t, let us call it as phi k of t. How can we create? E power j k omega 0 into t, where k is varying from 0 to plus or minus 1 to plus or minus 2 to plus or minus 3, etc. It is going like that, right? So these are known as harmonic signals, right? Harmonic signals, right, of e power j omega 0 t. When k is equal to 1, the equation will be e power j omega 0 t, right? And when k is equal to 2, it is e power j 2 omega 0 t. When k is equal to 3, it is e power j 3 omega 0 t. Here you can see that the frequency is increasing. Frequency is increasing, right? So these are all harmonics. These are all harmonics which we have discussed in the Desmos, right? These are all harmonics. And you have to keep another idea in your mind that if t0 is the fundamental period of the fundamental signal e power j omega 0 t, right? E power j omega 0 t. If t0 is the fundamental period of that signal, then all the harmonics will be periodic with respect to t0, because it will start and end within this t0. It will be periodic. It will be periodic with respect to t0. You have to keep this idea in also in your mind, right? Now assume that any signal x of t can be expressed as a linear combination of k is equal to minus infinity to plus infinity ak into e power j k omega 0. Assume that a signal x of t can be expressed as a linear combination of complex exponential, right? So these are harmonics. Actually these are harmonics. When k varies, the harmonic value will increase. First harmonic, second harmonic. So we are trying to create a signal x of t which is a periodic signal, okay? So which is a periodic signal, right? So periodic signal using the harmonics of e power j omega 0 t, right? So this particular equation says that we can create an arbitrary signal, or we can express an arbitrary signal x of t as a linear combination of harmonically related complex exponentials, right? So these are harmonically related complex exponential, right? So when k is equal to 1, this is the fundamental frequency. K is equal to first harmonic, k is equal to 3 second harmonic, k is equal to 4 third harmonics, like that it will go up to nth harmonic, right? If k is equal to n, then it is nth harmonic, right? So by adding all such harmonics, we can create a signal x of t. Then that is the continuous time Fourier series of the signal x of t, right? That is the continuous time Fourier series of the signal x of t, right? The representation of a continuous time periodic signal x of t as a sum or as a linear combination of harmonically related complex exponential is known as continuous time Fourier series. So I am going to type the definition here for you. So if you can express any signal x of t as a linear combination, so from where the word linear combination comes, because you can see summation k varies from minus infinity to plus infinity, ak into e power jk omega 0 t. If we expand this equation, what happen? If we expand this equation, what happen? This will be a0 into e power j0 t plus a1 into e power j omega 0 t plus a2 into e power j2 omega 0 t plus a3 into e power j3 omega 0 t. These are all harmonically related complex exponentials, right? So by adding such harmonically related complex exponentials, if we can create a signal x of t, right, then that is the continuous time Fourier series of the signal. The equation says that a periodic signal x of t with the period t0 can be expressed as a sum of complex exponentials e power j omega t and its harmonics, right? So what is the definition? The definition says that any signal x of t can be expressed as a linear combination of e power j omega 0 t and its harmonics, right? And its harmonics, right? So how to express it mathematically? X of t is equal to summation k equal to minus infinity to plus infinity ak into e power j k omega 0 t. The heading is continuous time Fourier series. Where is the series? See, this series on the right side of the equation is known as the continuous time Fourier series, right? So it says that you can express the signal x of t as a series, right? It is a series. If you expand this, you can get a1 e power j omega 0 t plus a2 e power j2 omega 0 t plus a3 e power j3 omega 0 t, like that. This is a actually this is a continuous series, right? So this infinite series on the right side of the equation is known as CTFS of the periodic signal x of t, right? And this is our actual signal. That signal is expressed like this, and that is known as the continuous time Fourier series representation of the signal x of t.
I hope you got a clear idea about the beautiful formula of continuous time Fourier series, which says that any periodic signal x of t can be expressed as a linear combination of complex exponential signals, which are the eigenfunctions of the linear time invariant systems.